Okay, so example 3. Suppose the North Carolina Division of Fisheries has ascertained that the population of a certain species of fish in Bogue Sound can be modeled using the equation P of t equals 10e to the negative 0.12t, where P of t is the number of fish in thousands and t is time in years. And that's really that you pay attention to what your variables stand for in your function. The decision has been made that fishermen will no longer be able to fish for this species once the population reaches 8,000 fish. When will the population reach 8,000 fish? All right, so this part's really important, folks, because it tells you that the population is in thousands. And so when you're looking at this formula right here and you see that 10 as the initial value, it's not 10 fish, it's really representing 10,000 fish. So when we want to know when the population will reach 8,000 fish, we're not going to substitute 8,000 in. We will actually substitute in 8 since P of t is represented as thousands of fish. So we will substitute that in. 8 equals 10e to the negative 0.12t. Notice how the rate is negative because these fish are decaying or decreasing. So we're going to be solving this algebraically now that we have gone back through and learned about our logarithms. So the first step in solving this algebraically is to get that base isolated by itself. So to do that, we're going to divide each side by 10. And that will give us 0.8 is equal to e to the negative 0.12t. Now, since the base in this problem is e, instead of using log, we'll use natural log. Technically, you could use log, but if you do it, you're going to have to do a few more steps to solve it. So anytime it's base e, it's much quicker to use natural log. Base 10, it's much quicker to use log. Any other base, it really doesn't matter. All right, so we're going to take the natural log of each side, because what we do to one side, we must do to the other. That's this whole property of equality thing. By doing that, there's two ways you can look at this. Either you can drop the exponent down to the ground, and then the natural log of e is 1, or we're going to apply our property that anytime we have the natural log of e raised to, it doesn't matter what it is, I'm going to put a heart right there. They undo each other, and the answer is just that heart, because that's the whole idea. A logarithm undoes that exponential. So at this point, we have the natural log of 0.8 is just equal to negative 0.12t. And then to finish it out, we would divide each side by negative 0.12. And we will then type that in our calculators to get the final answer. So remember, your natural log button is right here on that first column of buttons. So we would just say the natural log of 0.8 divided by negative 0.12. And it gives us our answer. Let's say they wanted us to find out exactly from today how long that will be. Instead of saying it's about 1.859 years, what we could do is in our calculators, we know it's 1 year. So we could subtract the 1 from the answer that we have, and then that gives us the portion of the years that's left, and approximately there's 365 days a year, so we could times that by 365, and that would tell us, okay, around 314 days. This is the algebraic approach to solving these problems. Of course, we could, if we have technology, and you're allowed to use a graphical approach, we could always graph it in our calculator, and we could do this to check our algebraic work. But guys, for this lesson, I do want you to be using logarithms to solve it. The whole point is to practice using your logarithms and improve those logarithm skills. If we want to use a graphical method, we would just graph the function in our calculator and then graph the horizontal line, y equals 8, and find that intersection. So going back into our calculators, if we look at that, we go to y equals, we type our function in with x, and then come in here and add 8 and graph it, and then just hit your second trace, do number 5, your intersection. And we had some problems like this in the exponential part of our lesson, our notes this week, and you can see that you get the same answer as if we had worked it out algebraically. Okay, so going down to example 4, we are now solving exponential equations. And actually what we just did above with our fish problem, we were solving exponential equations. This is an exponential equation. And the first step in solving any exponential equation is get the base by itself. Folks, how we know this is an exponential equation is because the variable is in the exponent. So that's where we're going to start with this. We're going to start by subtracting 5 from each side, which gives us 4 times 2 raised to the 2x minus 1 is equal to 24. We would then divide each side by 4. So we get that 2 raised to the 2x minus 1 is equal to 6. Once we have gotten our base by itself, in this case our base is 2, we now can take the log or the natural log of each side. So anytime you have a problem that has base e, it's quicker and easier to take the natural log. Anytime you have a problem that is a base of 10, it's quicker or easier to take the common log. If it's any other base, 2, 5, 8, whatever it is, it really doesn't matter. You can take the natural log of each side or take the log of each side because the steps you're going to do is going to be exactly the same from this point forward. A lot of students will get just kind of, anytime it has e, they use natural log, and if it doesn't, they use log, and that's fine if that's how it works out in your head. Once we take the log of each side, that's what allows us to take that exponent in the air down to the ground so that we can finally solve for x. So that gives us 2x minus 1 times the log of 2 is equal to the log of 6. So now that we can solve for that x, that we've got it down to the ground, we're going to divide each side by the log of 2. So that then leaves us with 2x minus 1 equals the log of 6 divided by the log of 2. We would then add 1 to the opposite side, so 2x is equal to the log of 6 divided by the log of 2 plus 1. And then last but not least, we would divide by 2. Now, if we were to have to give an exact answer, that would be really ugly because it would be this big complex fraction. So remember, dividing by 2 is the same thing as multiplying by 1/2, so it might be easier to write it like this. We would just say 1/2 times the log of 6 divided by the log of 2 plus 1, and that could be represented as our exact answer. All right, so we're going to want to type these in our calculator, so we would say the log of 6 divided by, make sure you close out that parenthesis, divided by the log of 2 plus 1, and then once I get that, I'm going to divide the whole thing by 2, because that's probably what we would do if we were walking through it. One of the things I highly recommend you doing, especially when you do have your technology, is once you get your answer, store your answer for x, and then check it to make sure you didn't make a mistake. So I'm just going to retype in the left side of our equation, so that's 4 times 2 raised to the 2x minus 1 plus 5. And if we did this correctly, it should equal 29. And it does, so we know we're good and we can move on. So the first answer that we have is our exact solution, and the one we get out of our calculator is the approximate solution. And by the way, the problems that we are skipping through this lesson are the practice problems that we'll be working on together in class tomorrow. All right, so next, example 5. This is a logarithmic equation. So how do we solve logarithmic equations? So the first step for solving any type of logarithmic equation is to isolate the logs. In other words, condense the logs. Sometimes you might have logs on both sides. Sometimes you might only have them on one side. So in this case, we only have a logarithm on one side. Because this is an equation and we're not just trying to clean up this expression, this 3 in front, yes, we could put back up as the exponent, or we can divide through. And I think in this case it'll be a little bit easier if we would just divide each side by 3. And when we do that, we're talking about the coefficient in front, not the 3x inside. You cannot divide that from inside that logarithm. So that leaves us with the log base 2 of 3x is equal to 3. Okay, when we get here, there are two things we can do. We can either base it up or we can convert back to exponential form. I pretty much always base it up. That's what I do. If it's an exponential equation, once I isolate the base, I take the log of each side. If it's a logarithmic equation, once I isolate those logs, I base it up on each side because they undo each other. That's the whole idea of exponential and logarithms. They undo each other. So right here, because this is a base of 2, I'm going to 2 it up on each side. And I know that's weird, but that's what I mean by base it up. The reason why that works is because it undoes each other. It is that property that if we have log base b of b to the x, they undo each other. It's just x. So that's what's happening right here. So this 3x just pops out. And then on the right-hand side, I have 2 to the third power. And we know that 2 cubed is 8. We would then divide each side by 3. And we get that x is equal to 8/3. Another method that you could use for this particular example is you could have converted back to exponential form, because in this particular example, when you get to log base 2 of 3x equals 3, it only has the log on one side. So I'm going to write that up here. This would be method 2. Still use the same first step. We would divide through by 3, so we get log base 2 of 3x is equal to 3. But instead of 2ing it up on each side and basing it up, we could just convert it back to exponential form. Our base is 2. Our exponent is 3, equal to our answer, which is 3x, which we learned in the first part of our lesson. And then if you look at it, guys, it's the same thing we have down here, because 2 cubed is then 8, so 8 equals 3x. And when you divide each side by 3, you get that 8/3 is equal to x. They both work. It's just how your brain works and whichever way you would prefer to do it. Just make sure when you do these that you always check your solutions. Because logarithmic functions do not have a domain of all real numbers. Remember, a logarithmic function has a domain of only positive real numbers. You always have to make sure that if you were to substitute your answer back into the original equation, you would only be taking the log of a positive number. We cannot take the log of 0 or negative numbers, so be really careful about that. And in this case, our 8/3 is good to go. We do not have any extraneous solutions. All right, so we will be doing the next number 5 problems with our practice. So let's go to number 6. So number 6 is also a logarithmic equation, but in this case, it's not just one log. So the first step, look at your steps above, is we have to isolate and condense the logs. And if you have logs on both sides, make sure you do it on both sides. So if we look at these natural logs on the left-hand side, they do not have any coefficients. So since this is plus, we can go ahead and join this by multiplying. So we can make this the natural log of 2x minus 3 times x plus 2. Well, when we look at the right-hand side, we do have a coefficient of 2 right here, so we have to pop that back up as the power. So this is going to be the natural log of x squared. So when we clean that up and multiply those binomials, we're going to have the natural log of 2x squared, negative 3x and positive 4x gives us plus x minus 6 equals the natural log of x squared. At this point, we can now base it up on each side or apply the property of equality. So in this case, because we now have condensed it and we have a natural log equal to a natural log, property of equality says that what's inside them must be equal. We couldn't do that in example of 5 because we only had a logarithm on one side. Or we can base it up just like we did in example 5. The only difference here is when we base it up, and remember, because this is a natural log, the base is e, so I'm going to e it up on each side. They undo each other. E to the natural log of whatever, let's say of a heart, is just a heart. They undo each other. That's that whole deal with exponential and logarithms. So what's inside just pops out. So we have 2x squared plus x minus 6 is equal to x squared. And then we would work this out. So since this is a quadratic equation, we're going to subtract x squared from each side. So that gives us x squared plus x minus 6 is equal to 0. The factors would be x minus 2 and x plus 3. We set each factor equal to 0 and solve, and we get that x is equal to 2 and x is equal to negative 3. Remember, we always have to check our answers. If we were to substitute 2 right back here in this logarithm, 2 times 2 is 4, 4 minus 3 is 1, we can take the natural log of 1. 2 plus 2 is 4, we can take the natural log of 4, and right here that would be the natural log of 2. So as long as we're taking the natural log or log of a positive number, we're good. So this answer of 2 is good to go. We checked it out. However, if we were to substitute negative 3 into this first one, 2 times negative 3 is negative 6. Negative 6 minus 3 is negative 9. We cannot take the natural log of negative 9. It is not in the domain of our natural logarithm. So this answer is an extraneous solution. So in this case, we only have one answer. And that's why it's so important to make sure you always check your answers. And then we will be doing number 6 with our practice.